So our next speaker, who I should just introduce, is the last speaker in this session, is Jorge Monroy Ruz. I'm sorry if I've butchered your pronunciation of your name. And we're going to hear a bit more about diamonds, encapsulated nanodiamonds for NV center embedded silicon nitride quantum photonics. Awesome. So please take it away.
Okay, I don't know if you can see me.
Yes, sorry, yes.
Okay, I want to share my screen now. No, wait. And okay.
Great, you can see that.
All right. Okay, well, hello everybody. My name is Jorge Monroy Ruz.
Full screen.
Yeah. Full screen. Oh, give me a second. Is that working now?
Yes. Now it's yes.
Yes, in presentation mode.
Yep. Perfect.
Excellent. Okay. Yeah, thank you. I am I'm student in the University of Bristol. I'm part of GET Labs, the quantum engineering technology of quantum engineering CDT. So I would like to thank the organizers of BQIT for letting me present my work here. I would like to thank my sponsors, the Quantum Engineering CDT and the Mexico's Science National Council of Science and Technology, CONACYT, and also the BQIT team for all the effort you've put to deliver this workshop, given the conditions. So, okay, I'll be telling you about my PhD project. And I would like, well, the session with Connor's talk, you are somehow convinced that the NV centers are like have the potential to be in the core of quantum communications and quantum computation. His fantastic talk like showed us the power of these systems. So probably I don't need to tell you a lot about the motivation of why do we want to do use NV centers, but I would be telling you about like what do we see is an issue when we're trying to build like large scale devices using NV centers. So I'm briefly gonna tell about which are these issues, tell you about our platform, and kind of like split that project into the three steps, like the material we're using, how we put in the diamonds, and the device we're trying to do. Okay, so first of all, for you, for some of us attendees that might not be aware of what NV centers are or color centers in diamond are, they're basically defects in the lattice of diamond where some atoms are not carbon replace carbon atoms, and particularly in the NV center is a nitrogen that replaces the carbon atom and creates a pair of nitrogen and vacancy. And these systems they're very good because as Connor showed, like they allow us coherent control of the electron spin state using microwaves. They allow for coherent control of the of coupling with the nuclear spins around them, and also they allow for optical readout of the spin state, which is which is like it's in the visible range, well, visible near infrared, and if you focus on that bit, you need to recover those photons emitted by the NV center to know if what's the spin state of your system. And if you want to recover a photon in a high refractive index medium like a diamond, then you'll have a bit of an issue because of total internal reflection. But some of these issues have been addressed by shaping the diamond in some of these solid immersion lenses structures. Here's an image of some of the first ones done a few years ago here in Bristol, and people around the world, like I'm maybe Connor will correct me if I'm wrong, but I think like the experiment he showed is using one of these solid immersion lenses, and yeah, so that's still something that is used around the world. That's not the only way. People in Harvard have these amazing have showed these amazing devices where they manage to undercut diamond and suspend these nanobeams to create 1D cavities of diamond with color centers in the middle of them. However, I think it's debatable how scalable this is. Like it's well known that it's a quite difficult process. So if you want to have 1,000 qubits, 1,000 of these defects, and probably connect them, probably these solid immersion lenses or this diamond etching is not like a very feasible solution. So in order to address that, people have moved into using well, an alternative is to use nanodiamonds. And what we mean with nanodiamonds are nanoparticles of diamond, which contain probably one, like hopefully one of these defects, and then use those nanodiamonds on top of other material platforms. So an example of this, like about 10 years ago in Oliver Benson's group, they managed to put one of these nanodiamonds in the center of a gallium phosphide photonic crystal cavity by pushing it with an AFM tip and putting it in the center of the photonic crystal cavity. Here's another image from a couple of years ago, 2-3 years ago, on David Hunger's group, where they enhance the single photon emission of silicon vacancies in nanodiamonds using these fiber-based cavities. So yeah, it's possible to do it with nanodiamonds, but as you can see here, if you again are thinking of 1,000 MV centers, I don't think like pushing a fun job to do. So with this in mind, we're trying to, okay, so how can we build bottom up platform that allow us to use all these richness of the MV center, but without with this scalability issue. So our approach is to embed nanodiamonds in silicon nitride. So this is roughly the procedure where like the fabrication procedure to create this, which is we start like with very few silica. We put some silicon nitride on it, then we disperse some nanodiamonds, cap them with more silicon nitride, and then etch the silicon nitride to create our photonic devices like waveguides, cavities, ring resonators, whatever we want to do. So I'm going to be presenting results on the first 5 steps of this process and some preliminary results on the last one. Okay, so yeah, why silicon nitride? Well, first of all, we need a material that is transparent to the emission of the MV centers. So silicon nitride, like it's transparent at those wavelengths, but also it's a CMOS compatible material. That means that has been a lot of research and a lot of design on very like good performance devices. So seems to be like a very straightforward material to use. However, there's a big issue with this. So if you use stoichiometric silicon nitride, you would find they would be very noisy, and it would be very noisy in the terms of when you use these green, blue, or yellow lasers. They will be exciting a lot of states in the silicon nitride, and its autofluorescence, its fluorescence will be creating a lot of noise because it emits in the same band as the MV center. So that was the first problem we tried to tackle. And it's well known in the literature that if you move the stoichiometry of the silicon nitride, you would move these autofluorescence. So we use plasma-enhanced chemical vapor deposition, PECVD, to create films with different stoichiometry. So for those who don't know what PECVD is you put your substrate in a vacuum chamber, you put some gases, you strike that with a high power radio frequency. Plasma creates particles that, well, what we did is we created films with different stoichiometries, like by changing the ratio between the silane and ammonia, and measure the autofluorescence of these films. So this is the first one. So this R parameter is the ratio between these two gases. So you would say that this is a silicon-rich film. And as you can see in the curve and the red curve, fluorescence is quite high. It's comparable to the stoichiometric boundary available silicon nitride. But then when you start increasing that parameter, that means increasing the amount of nitrogen in the film, you can see that the fluorescence starts to get suppressed. And then you can reach to a point here where the fluorescence is comparable to the background that just comes from the setup and the scattering from the fused silica substrate. So this is assumed to the same spectrum, and this is the R equals 7, which is like pretty similar to R equals 3. So yeah, this is kind of like a summarize of that. So you look at the purple curve, you can see the integrated spectrum of the autofluorescence of the silicon nitride. You can see exponential decay at the bottom, and you can also see how the refractive index changes as expected with this stoichiometry. So the recipe or the parameter we're going to pick is the one that suppresses the autofluorescence but does not compromise too much the refractive index, so we can have like a better footprint and better performance of the devices. That's why we picked this R equals 3 recipe, and that's what we did. We capped some nanodiamonds with it. So this is a confocal image of dispersed nanodiamonds in the fused silica substrate before getting capped with the silicon nitride. We measured some of these MV centers. We can locate them because we have some of these auxiliary markers, and then we cap the same sample and go back to exactly the same place and measure the same MV centers. And we can see that we can recover like the single photon behavior of the not completely, but enough the background fluorescence to observe single photon emission, and we can preserve. Well, the lifetime gets suppressed around 3 times. That's due to the change in the refractive index, the MV center fields. We also did some coherent drive of the electron spin, and we can see that these drive annotations, how even when the coherence time, the T2 star, like gets reduced, it's still over the threshold to do these dynamical decoupling, like Connor was explaining early in the session. So cool. We can cap these nanodiamonds. We can still see the MV centers. They don't get too affected. Obviously, there's still some noises and add some charge noise, and but still things that we need to study. However, I would like to point something out. Like for the experiment, we dispersed the nanodiamonds in a random fashion, and obviously, if the main motivation of this work was the scalability. Well, that's clearly not scalable. However, we wanted to address this other issue, and about a couple of years ago, we came across with this paper of Ashley Heffernan and Brant Gibson in Australia, where they used this mask of holes to just arrange the nanodiamonds in these like lattice of sites with nanodiamonds, and we thought, well, that's very cool. I don't think that's going to work, but it's very cool. And it's surprisingly worked very well. These are some CM images of our arrays of diamonds diameters. So you can see here like holes of 3 micron diameter with many of these nanodiamonds. But then when you reduce the diameter size, you start getting to the regime where you deposit single or probably a couple of nanodiamonds, which makes us kind of enables us to start like thinking, okay, now we can deposit them where we want. Now then we can start planning on which devices we want to make. So yeah, so now we are starting to work on which devices I want to make first. Oh, sorry, I went too fast. So I just want to show you yeah, so like the confocal images of these arrays, and we can start like doing other kinds of characterizations. So for example, we can see how is the distribution of orientations given. So you can excite these differently and emit brighter with certain polarization. So that gives you information of the orientation of the SMB center, which is an important bit of information if you want to optimize the coupling to any device you want to fabricate around them. So I lost track a little bit of how much time do I have left. I think I still have like five minutes or so. So yeah, I just quickly wanted to show you which are the first devices we're planning to do. So we, as you see, we can put the nanodiamonds actually, but there's still some diameter of the hole, and also like the MV, the defect within that nanodiamond is something we don't have control on. So the first device we wanted to try is something that is a bit more resilient to position. So we don't want to jump directly into a super high Q cavity. However, we found like this recent trend of doing these bullseye cavities. So this is an image from last year's a paper last year from Jiang Wei Pan's group, where they are doing these cavities in indium gallium arsenide quantum dots. And we thought, okay, why don't we try to recover that, given the fact that the central disk is hundreds of nanometers, like it's almost a micron. So we did some simulations, and then we are in the process of trying to this image of the was taken around 3 days before the lockdown, so I don't have image. But yeah, that's the direction we're trying to go now. We have also done some tests. Some we have fabricated some waveguides, but we still don't have any figures on the loss of these low fluorescence silicon nitride. But yeah, that's the direction we are heading to. So in summary, I would like to conclude saying that hopefully I kind of communicated how important it is to look for a solution for this scalability, because these color-sensitive diamonds are really, really powerful and robust systems for quantum information technologies. However, we need to find a way of making, like putting many of them, and if we want to communicate many of them, we need to find a way of making this in a scalable fashion. So I have shown you that nitrogen-enriched silicon nitrates, it's a viable platform for that. We can deposit arrays of these nanodiamonds, so we can start like creating tens or hundreds of devices and test them quite easily. And finally, I show you some of the progress of we have done in fabricating our first devices. Just finally, I would like to thank my supervisors, Krishna Kombatore Balram and Professor John Rarity, my partners in crime and my teammates, Joe and Cecile, and also I would like to thank Bisu and Andy Murray in the clean room that have helped me a lot to make these devices. And that's it. Thank you very much for listening.
Great. Really, thanks very much. Another really fantastic talk, super interesting. So I'll just yeah, you finished very early as well. But before everyone runs off for a cup of tea, there are just one or two questions. Let me see. Oh yeah, so one question from Ralph Riedinger is the NV0 phonon line width influenced by the nitride deposition?
The zero phonon line width. Well, it wouldn't be affected by the nitride deposition. It certainly would be like if you do well, the emission rate would change because it sees like a different refractive index. This is like a different medium. But the refractive index, the line width itself, I don't think it would be too affected because you have like this shell of diamond still around the NV center. It might be shifting a little bit by charge. So there's like these spectral diffusing because of charge drops. But that's something that we haven't characterized well because all the results I show you today, all that is at room temperature. So we're starting to, I don't think we predict temperatures.
I think you just said, you dropped out for a second, but I think you just said everything was at room temperature.
Yes, that's
right,
what I said, yeah.
Right. Yeah. Well, actually, maybe a related question was, is the phonon spectrum that interacting with the NV affected by the fact that you're in a nanodiamond? I know that sometimes nanodiamonds are considered useful for silicon vacancies because they modify the phonon spectrum there. But is that something that you see in the? Maybe the answer is the same. But do you expect to see a modification of the density of states of phonons?
Yeah. So it's true that the nanodiamonds have like a more variety of stresses and can use different different stress in different directions and that affects the coupling to phonons. So again, like I think that's due to the nanoparticle rather than to the matrix we're like embedding the nanodiamonds in. And so one thing we found very useful of doing these arrays is that we can now very like a lot faster identify which ones are the which nanodiamonds are the ones that have we would be able, once we are in cryogenic temperatures, to identify which ones are the ones that have less stress, and we can pair like, okay, so these nanodiamond here and these nanodiamond there are quite similar, so enough to tune them with Stark shift, or so we can discriminate a lot faster now that we have these arrays. Very
cool, very interesting. So actually, since the end of your talk, there have been questions flooding in, so there are lots, but we've run out of time in this session. So yeah, you should everyone should head over to Slack, and maybe you can continue the discussion there.
Sure. Yeah, absolutely.
Thanks very much, Jorge. And